Hello, I want to spend a little bit of time going over misconceptions. So I didn't use the word physics misconceptions here. I'll give some examples, of course, from that. All the examples, well, all but one, silly one, will be from that. But the what pretty much everything I'm saying is appropriate for misconceptions in many fields, perhaps all fields. Three main topics. One, causes of misconceptions. Spend a little bit of time on that. And then recommendations for helping revise misconceptions or remediate misconceptions, um, change misconceptions. Pick the word that you think is appropriate, and then I will share some resources with you. So, causes of misconceptions. One cause, and some people might even argue that this wouldn't even be a misconception per se, but I think with a strict definition of the term, it's a conception that doesn't match reality. This is a misconception, and that comes from lack of knowledge, lack of prior knowledge. If you were to ask me about knitting, I would have all sorts of crazy things to say about knitting. Right now, I don't remember if it's knitting or crocheting that uses one needle or two, and one of them has a little hook at the end. So I don't know about that. If you asked me about knitting, I'd probably be describing crocheting or some combination between the two. Um, Typically, these type aren't as logistically difficult to remediate because if you have a misconception because you don't know about the topic, then knowing about the topic is often going to help address some of those misconceptions. So I wasn't sure what to use there. I said it's not as logistically difficult to remediate, but it may take a lot of time to address because a lot of my knitting misconceptions will be taken care of with some knitting lessons, but knitting lessons take time. Typically, though, when you think of misconceptions, and most of the misconceptions literature in physics education research is about not necessarily lack of prior knowledge, but inaccurate prior knowledge. And that can be a combination of lack. It could be that you learned something incorrectly. It could be that it's a complex topic. There are a lot of things that go into it, and you just aren't quite sure, and you're trying to sort out the different variables, the different parameters that go into a topic. So with that, there are really two types: straightforward concepts, and those can be more easily remediated with instruction. And towards the end of this presentation, I'll talk about quote unquote instruction and what are some ideas behind that. And then probably the thing that most likely comes to mind are deeply ingrained concepts, those things in which you know your students have quote unquote learned something, but they still aren't sure. The force concept inventory, which we use in the Physics 111 series at Central, that is a great example of that. The questions on there are great examples. They're fairly straightforward questions, fairly straightforward concepts. They're not mathematical. They're things that pretty much everybody's familiar with. Small cars colliding with big trucks, people pushing off a wall like a diver or a swimmer pushing off a wall, things like that. But still, people have these deeply ingrained understandings that don't match reality. So let's look at some examples here. One example is speed versus velocity. So this is a problem from the OpenStax College Physics book. Basically, someone's starting at home, they go 3 kilometers to a store, and then they come back. And then the question is about what is their average speed, what is their average velocity. We can look at a position versus time graph. And so the position versus time graph, it says here, the average speed is a certain rate. So the position versus time graph, the first one here, is showing, and let me make get a little pen. So it is showing the position. So they start at home, that's 0 on the number line, and then they move to something 3 kilometers away. And the assumption is that they're going at a constant rate. And I won't use speed or velocity, I'll say a constant rate. So then they do their, well, actually, they don't really do their thing at the store because there's no time at the top. They must have got to the store, and right when they pushed the door to go into the store, they realize, oh, I forgot my credit card or I forgot my wallet. I need to go home. So they immediately turn around and go home. A velocity versus time graph, you can construct that in a few different ways. For one thing, it says the average speed is 12 kilometers per hour. So if we assume going from home to store is the positive direction, then this first part is going to be positive 12 kilometers per hour. And then the person turns around virtually instantaneously, and then they go back home at 12 kilometers per hour. But since they're going in the opposite direction, and if we define the direction of home to store as positive, then store to home would be negative. We could also look at it in terms of the slope. So here the position versus time graph has a positive slope, rise over run, change in position. So we change in time, that equals velocity. So that's the rise over the run using that terminology. And then we get the velocity versus time graph. If we look at speed versus time, notice that is a flat line because the speed doesn't relate to the direction. It's just distance traveled divided by time taken. And in both cases, the same distance was traveled, the same time was taken. So the first and the second half speed are the same because speed is not affected by direction. This is something then that it's not zero complexity, but it's a little bit less complex than the next example I'm going to give. Because if students understand that two things, one, that speed is independent of direction. So we can't have two different speeds if the rate was the same going from home to store and store to home. And then also it's a definitional thing. So the velocity for the whole time, change in position, like right here, is 0 because they start at home, they end up at home. So that means the average velocity is going to be 0. We can also see that from, and I know I've got a lot of circles here now. We can see that from this. We've got a 12 kilometer per hour line segment and a negative 12 kilometer per hour line segment. They're both the same length, those line segments, so those are going to average to 0. Here, the two line segments are both 12 kilometers per hour, which means they're not going to average to 0. They're going to average to 12 kilometers per hour. The Institute of Physics, a British organization, has some great information about this. And we'll discard those. And this is the generic phrasing of that. Many students conflate velocity with speed. So this describes that, gives you some diagnostic resources to help you see if this is something that your students have a belief in, and then a way to address this. So these are hot links here and hot links here. And this there's a URL here that is actually hiding behind my picture. It just says IOP page about this. So here's another example of inaccurate prior knowledge, forces acting on a ball tossed in the air. So here's a basketball being tossed in the air. Someone at the bottom here is about to throw it up in the air, and then we've got a little time lapse, just 3 images of the ball. And if you were to ask students to sketch the forces acting on the ball tossed in the air, the significantly sized forces, so we'll assume that air resistance is not a significantly sized force, what would your students draw? So think about that for just a few seconds. What forces, if we have to represent those forces with arrows, how would we draw those arrows? So there's definitely a downward force, the gravitational pull of the Earth on the ball, and that's it. If we say that air resistance is too small, a lot of times in physics courses or other courses too, they'll talk about neglecting air resistance or ignoring air resistance. That's probably the worst one, ignoring air resistance, because air resistance is there. We can't ignore it. Neglecting is a little bit better, because neglecting kind of implies that, well, we know that it's small, so we're not going to factor that in. If you are putting a trailer on the back of your vehicle and your vehicle has a certain towing capacity, you put the trailer on there and the trailer's near that towing capacity, and then you realize, oh, I forgot to put my, what would be something small? Oh, I forgot to put the map, because you got the map on your phone, but you wanted to bring another map. I forgot to toss the map in there. So you toss the map into the trailer. You can neglect the map's mass. So in the same case, you can neglect the air resistance. According to one study, John Clement at the University of Massachusetts, published in 1982, he surveyed students, and people have done this throughout the ages, makes it sound like some grand history, but throughout time. And his information showed that before instruction, 12% of his students got this right. The vast majority of the non-12% said that there was an upward force on the way up and then a downward force on the way down. So Professor Clement, University of Massachusetts, Amherst, it's a great public university. He's a great teacher. They're all great students. So after instruction, going to have big changes. Well, after instruction, 28% of the students got it correct. So that's way more than a doubling, but we don't need to do any fancy mathematics to find out that that still means that 72%, nearly 3/4 of the students after instruction, still got this wrong. So the word behind my face there, it says this, got this incorrect. So this is definitely defined then as a deeply ingrained concept. Still, a lot of students have this belief. In fact, nearly 2/3 of a good collection of college students. So there's an IOP page about this as well. Most students think if an object is moving, there must be a force in its direction of motion. So when the ball's going up, the force must be up. When the ball's coming down, the force must be down. So again, some resources to address this. This didn't have a little quiz that you could give your students, although you could actually give them the question that I raised on the slide there. And then some references. This is actually a different paper here. It builds on the one in which I got the 72% number, but you can look that up. And then a few more, lots of papers actually about this one. So the big news then is, let's talk about revising misconceptions. I've got 4 main points that I'm going to make here. And the first main point is you and your students need to identify and assess the conceptions. So maybe the word misconception should go with identify, and assess should be conception, but whatever. So you and the students, Physport.org is a great resource for a lot of different types of assessments. The force concept inventory, which we use in Physics 111, can be found here, as can concept inventories from many other physics areas as well: electricity and magnetism, energy, momentum. And the reason for that is if we don't know that we have a certain conception, if we've never articulated it, we've never thought about it, then we can't change it. And I put quotes around that because I just made up that statement and I wanted to turn into a famous quote. So we cannot change what we have not realized we are doing or believing. Bruce Palmquist, July 9th, 2025. And of course, the same thing with in life too, right? If we don't realize that we have a certain bad habit, then we're not going to change that habit. If we curse more than we should, especially around our kids, if we don't realize we're doing it, then we can't change that. If we're eating poorly and we don't realize that, we can't change it. Cursing around the kids, eating poorly, those are things you want to change before you change the direction of the force, your belief on the direction of the force of a ball. But still, same thing holds. Another thing you can do is a comparison table. So I have an example of a comparison table here. And depending on how you're looking at this, I'm going to actually change this around a little bit and move this up. Not going to need that anymore. Need that. All right, so we've got our two beliefs here. Let me make this a little bit bigger. So one belief is the upward force on the ball way up. So this is the comparison table for the ball. And you don't have to use these exact headings, but these are just some things to think about. So presenting, you could present this completely as is, or you could start with each belief here, each belief, and then have the students craft the rest of it. So I'm giving you a finished product here. Well, my version of a finished product. With the ball, when the ball's going up, the force acting is upward. When it's going down, the force acting is downward. Another belief is that there's a downward force throughout the motion. The assumption, so if there's an upward force on the way up, downward force on the way down, we're making an assumption that's actually the same for both of them, and that is basically the definition of forces. Forces are interactions between objects. But now the rest of the table is going to be different. So what's the implication here? If the forces are interactions between objects and the force changes on the way up and the way down, then the object interacting with the ball changes. Either it changes to a different object or something fundamentally changes about that object, because the ball's not changing. The ball's just being the ball. But if we think about what is the object that's interacting with the ball, well, that's the Earth. So the Earth must be changing, or a new force is popping in for the way up and on the way down. Maybe one of those forces stays the same. The Earth is the same in both cases, but something else is there when the ball is going up. The implication of downward force throughout the motion is that the object interacting with the ball stays the same, meaning the same object, and then that object does not change characteristics in any way. So then we can use some physics vocabulary on this. For the belief that the force changes up versus down, then if we use physics vocabulary, we're saying that force is in the direction of motion. If we say that there's a downward force throughout, then we're saying that force is in the direction of the acceleration. Because as the ball's going down, it's speeding up in the downward direction. So certainly makes sense that when the ball is falling down, the acceleration is downward. But when the ball's going up, it is slowing down. So it starts off as fast and ends up near the top of the motion as slow. So that means that the ball's acceleration on the way up is down. The ball's acceleration on the way down is down. And oh, look, that box in the lower left-hand corner, a downward force throughout the motion. Well, what are some applications of this if we take this to a natural conclusion? Well, if we say that force is in the direction of motion, if I hit a wall, so I walk into a wall, or I swing my hand or something like that and hit the wall, if we go by the forces in the direction of motion, well, hitting a wall can't hurt because the wall force is not in the direction of motion. If I'm hitting the wall, I'm moving towards the wall, always moving towards the wall. But the wall force has to be pushing away from my fist, so that it certainly isn't pulling my fist towards the wall. If it's doing anything, it's pushing my fist away from the wall. Maybe you could say the wall is not doing anything. And if that's the case, then of course the wall can't hurt my fist when I hit it. The implication of force is in the direction of the acceleration, then hitting a wall hurts because the force of the wall causes a rapid deceleration or a rapid slowing down of my fist. So with that application, you can ask the students, what is it? Hit your fist against the wall or against the desk. Does it hurt or not? Don't tell them to do it super hard, but it hurts. So the last column is giving us a real world application. If hitting a wall hurts, then that is evidence against the force changing on the ball on the way up and on the way down. We just did that. All right, so next few things here. And I just realized with this, I won't have to move my picture, but I will change things around for the second one. So one thing is to teach according to your lesson, follow a predict, observe, explain cycle. So for the predict part, the teacher presents a scenario. They do a demonstration. They tell a story. They show the first part of a video clip. And then students predict the outcome. So that's the predict. Second step, the teacher runs the scenario. And I guess the predict actually would come maybe sometimes in the middle of the scenario. So if you're showing a video, you play the video up until the part in which there is the potential for the misconception. You stop it, students predict. And then, so when the teacher runs the scenario, they play the next part of the video. But then the students observe the results. So they've made a prediction, they've observed the results, and then they compare their pre and post answers. And by doing that, they can describe and resolve the discrepancies. And they can try to explain what went wrong, or the teacher can try to explain. Best if the students try to explain it first, and then the teacher uses that information for their explanation to maybe clarify, use some of what the students say, and then clarify it into a class agreed upon explanation. And we've got that famous quote that we just learned about 10 minutes ago. We cannot change what we have not realized we are doing or believing. So that's why showing students something, having them predict, because if they don't predict, students and people in general are less likely to pay attention. If you've made a prediction, you've got a stake in the outcome. That's unfortunately why sports gambling is pretty popular, because people feel they have a stake in the outcome. Another teaching method is generically called refutational teaching. So I will shrink this up again. And with this type of teaching, so I don't really have a method here, but these are just some points. And the refutational teaching goes hand in hand with this predict, observe, and explain. It also goes hand in hand with the chart that you made that I went over on the previous slide. The students need to be dissatisfied with their current conception. Showing different conceptions together, like the table showed on the previous slide, students can see those, and the end result, once we get to the right-hand column, was one description of the ball results in hitting the wall. The conclusion needs to be you hit the wall with your hand, it doesn't hurt. Another one, the conclusion needs to be you hit the wall with your hand and it hurts. So if your view of the ball results in a belief that when you hit your hand against the wall, it shouldn't hurt, but you know it does, then you're dissatisfied with your current conception. And then you need to be presented with a plausible alternative. So just saying that's wrong is not going to be helpful. So presenting a plausible alternative. And for the predict, observe, explain, when students are comparing their pre and post answers, presumably not every student in the class have the same conception. So you're hearing other students give plausible explanations and intelligible explanations that you as a student, or the student who has a different view, can then say, oh, okay, I agree with that, or that seems reasonable. And also the alternative conception needs to be seen as beneficial. And beneficial, in the grand sense, means that the new explanation has more power than the old explanation. The new explanation helps you do things better, and maybe it just helps you answer physics questions better in class. That's not the greatest motivation, but it's better than zero motivation. The explanation needs to help you construct something better, utilize a tool better, for example. So those would be descriptions or examples of beneficial. And for the last slide, this is just some resources. One of them, and this presentation here, is taken mainly from the website Taking Learning Seriously. It's a great overview of misconceptions and, like I said, the basis of this presentation. The American Psychological Association has a very detailed overview of misconceptions, how they come to be, and how learning theory relates to that. And this is not a blob, it's a blog. So the Institute of Physics blog, spark.iop.org, and they have a great misconceptions page. But this link specifically is to a very long article that really is helpful in planning. Curriculum to avoid and revise misconceptions. So this, the IOP, Institute of Physics, this would be a great place to look if you want to overhaul the ways that you're teaching some things. They give you a lot of great information on that. Thank you.